Hello there, and welcome to the Sleep with Science. Tonight, we drift back to the very beginning of everything we know. Long before stars ignited or galaxies began to turn, before time found its rhythm and space took on its shape, the universe began its long and mysterious journey. The Big Bang is not simply a single moment frozen somewhere in the distant past. It is an ongoing story, still written across the night sky, carried by ancient light and echoed in the deep structures of the cosmos. This is not only a journey into our origins, but also into our connections. The atoms within you share a lineage with the earliest moments of the universe. The same laws that shaped the first galaxies continue to shape the world around you even now, in this very moment. As we explore this vast beginning, we will move through mind-bending discoveries, while uncovering mysteries that still remain beyond the reach of science. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here as well, one sleepy soul at a time. For now, there's nothing you need to do but relax. Allow your body to soften, your breathing to slow, and let the day quietly fade away as we explore the origins of the universe together. Let's begin. The Big Bang does not actually describe a bang. Instead, it describes our universe expanding from an extremely hot and dense beginning. What makes this idea so powerful is that it is not a myth or a guess. It is a model that brings together several very different clues into one coherent story. When we look outward, we see that distant galaxies have light shifted toward longer wavelengths, and this shift increases with distance. That pattern fits perfectly with an expanding universe. When we measured the faint background glow of the sky, it matches what a once hotter universe should have left behind. And when we examine the lightest elements in ancient gas, their proportions align with what a young, hot cosmos would have created. Taken together, these lines of evidence transform a bold origin story into something testable. The Big Bang is not just a beginning. It is a framework that continues to be checked against the sky. It was not an explosion within space. It was space itself expanding. In an ordinary explosion, debris flies outward into an already existing space. But this beginning was stranger. The space itself grew. That difference explains why there is no special center to point to and no edge you could travel toward. Every region sees other distant regions moving away because the distance between them is being stretched. This also explains why very distant galaxies can appear to move away faster than the speed of light without breaking relativity. Nothing is outrunning light through space. Instead, the scale of space between distant places is changing. This idea reshapes how we imagine the early universe. It was not matter bursting outward from a single point. It was an everywhere that was once smaller, hotter, and denser, expanding and cooling as a whole. The universe began as a smooth fireball, and over time it grew structure. At first, the cosmos was remarkably uniform, with energy and particles spread almost evenly. If it had remained perfectly smooth, nothing interesting would ever have formed. Gravity needs tiny differences to amplify. And here lies a remarkable twist. The early universe did contain small variations, and we can still see their fingerprints today. They were incredibly slight, yet they were enough. Over immense stretches of time, denser regions pulled in more material, becoming denser still. That runaway process built structure from almost nothing. The small irregularities grew into gas clouds. The clouds formed the first stars. The stars gathered into galaxies, and galaxies assembled into clusters. When you look at the night sky, you are seeing a mature version of those faint early variations, magnified by gravity into a universe full of form and structure. The oldest light we can observe still fills all directions even today. This light began its journey when the universe cooled enough for electrons to settle into atoms. Before that moment, free electrons constantly scattered light, making the cosmos resemble a glowing fog you could not see through. Once atoms formed, light could travel freely across vast distances. Those ancient photons have been moving through space ever since, and they continue to reach Earth from every direction. Time has stretched their wavelengths. What began as hot, visible, or infrared light now arrives mostly as microwaves. By studying this all-sky glow, scientists can read a snapshot of the universe when it was still young. It is not a picture of stars or galaxies. It is a picture from before they existed, and it allows us to test ideas about how the early universe behaved. This afterglow is colder than deep space, yet it is everywhere. Today, that ancient background radiation has cooled to just a few degrees above absolute zero. Empty space is often described as cold, but this faint radiation sets a real temperature floor that fills the universe. It is invisible to our eyes, yet incredibly precise instruments can measure it. It even appears in an unexpected place. A small portion of the static on an untuned television has the same cosmic origin, arriving after a journey that began long before Earth itself formed. This afterglow is also astonishingly uniform, suggesting that the early universe was well mixed. At the same time, it contains tiny variations that act like a map of primordial conditions. In this sense, the coldness is not emptiness, it is information. For a brief period, the universe was hotter than the core of any star. While the hottest stellar cores reached tens of millions of degrees, the early universe was vastly hotter still. At such extreme temperatures, atoms cannot exist. Even atomic nuclei cannot survive. Matter becomes a seething mixture of fundamental particles and radiation, constantly interacting. In this environment, familiar distinctions blur. Energy transforms into particle pairs, and those pairs can turn back into energy. The cosmos is not a collection of objects. It is a constantly changing state of physics itself. As expansion continued, the temperature dropped, and the range of possible particles changed with it. Some became rare, others froze out and remained. That is why early conditions matter so much. The particle physics of those first moments helped determine what ingredients the later universe would have. When we build high-energy experiments on Earth, we are not just smashing particles. We are briefly recreating echoes of that primordial heat. In the first minutes, the universe forged most of its helium. Helium is often associated with stars, yet a significant portion of it was created long before the first star ever ignited. As the universe cooled from its earliest heat, protons and neutrons began to combine. This happened within a very narrow window. It was still hot enough for nuclear reactions to occur, yet cooling rapidly. Within just minutes, most free neutrons became locked inside helium nuclei, because helium is especially stable. That is why roughly a quarter of the ordinary matter in the universe today is helium. Even in regions with very few generations of stars, this same pattern appears. The early universe also produced small amounts of deuterium and traces of lithium. These abundances are not random. They depend on the density of ordinary matter in the young universe. That is why measuring light elements in ancient gas allows scientists to test the Big Bang model with remarkable precision. Every atom in your body traces back to this early cosmic history. Some of your atoms have a lineage that begins in those first minutes, when hydrogen and helium became the universe's first long-lived building blocks. Many others arrived later, formed inside stars that lived, aged, and transformed. Carbon, which anchors your biology, was created in stellar furnaces. Oxygen was forged in massive stars and released when those stars died. Iron, which carries oxygen in your blood, was born in violent stellar endings. Even rarer elements, like those found in jewelry, are tied to extraordinary cosmic events where atomic nuclei are forced together under extreme conditions. None of these stories replace the earlier one. They build upon it. The early universe provided simplicity. Later generations of stars added complexity. When you hear that you are made of star stuff, it is true. But it is only the middle of a much longer story. Tiny early ripples grew into galaxies, clusters, and vast cosmic webs. These initial variations were not random bumps. They followed patterns that modern observations can still detect. Ordinary matter alone would have struggled to clump quickly enough because radiation pressure resisted collapse in the early universe. An invisible component, interacting mainly through gravity, provided additional pull and helped structures form earlier and faster. Over time, matter streamed into denser regions, and vast filaments stretched between enormous voids. Galaxies formed along these filaments like beads on threads, and clusters emerged where those threads intersected. This large-scale structure is one of the most striking results of simple gravity acting over immense time on tiny beginnings. It also serves as a vast laboratory. By mapping the distribution of galaxies and how it changes with distance, scientists can test how fast the universe expanded and how strongly gravity shaped its evolution. Our very existence depends on a slight imbalance between matter and antimatter. In the early universe, energy created matter and antimatter in pairs, and those pairs could annihilate back into light. If equal amounts had formed, almost everything would have cancelled out, leaving behind only radiation. Instead, for reasons still being investigated, there was a tiny excess of matter. After most annihilations were complete, that small leftover became the material for stars, planets, and life itself. This remains one of the deepest open questions in cosmology because it connects the largest structures in the universe to the smallest rules of particle physics. The universe needed processes that treated matter and antimatter slightly differently, and it needed the right conditions for that difference to matter. Experiments continue to search for these subtle asymmetries, while cosmologists look for clues in the sky. The simple fact that anything solid exists at all is evidence that the early universe favored matter, even if only slightly. Timekeeping for the universe is based on expansion, not clocks. Instead of counting years in a conventional sense, cosmologists read the universe like a clock built into space itself. They measure how fast galaxies move apart at different distances and how that rate has changed over time. Expansion leaves multiple traces. It stretches light from distant galaxies and sets the scale of patterns formed in the early universe, patterns we can still observe today. When independent measurements agree, they reveal a consistent timeline for cosmic history. That is how we can estimate the age of the universe, even though no one was there to witness its beginning. This is also why debates about the exact expansion rate matter so much. Even a small difference today can reshape our understanding of the past and hint that something may be missing from our current model. The early universe was so dense that light could not travel freely. Imagine trying to see through a storm, where every beam of light is scattered instantly. In those earliest moments, space was filled with fast-moving charged particles, and photons constantly collided with them. Light existed, but it could not carry an image across any meaningful distance. The universe behaved like an opaque, glowing fog. This detail is crucial because it means there is a natural limit to how far back we can see. We cannot observe earlier than the moment when conditions changed and light was finally able to travel freely. Before that, the universe was not dark. It was too bright, too hot, and too dense to be transparent. This early opacity also influenced what could form. With radiation tightly coupled to matter, pressure resisted gravity, delaying the growth of structure until the universe cooled and expanded enough. Then, something remarkable happened. When atoms first formed, the universe suddenly became transparent. It was like a curtain lifting. As temperatures dropped, electrons could finally remain bound to nuclei instead of being torn away by energetic collisions. Once matter became mostly neutral, photons stopped scattering constantly and began traveling freely through space. That transition released the oldest light we can observe today. It also changed the behavior of matter itself. Neutral gas behaves differently from ionized plasma. Pressure decreased, cooling became more efficient, and gravity could more easily gather matter into dense regions. This moment shows how a microscopic change can reshape the entire universe. It is also why the early universe can be studied like a fossil. A single transition left behind a sky full of information,
still measurable with precision. Hydrogen formed first, then helium, and only a trace of lithium. This simple chemical beginning shaped the universe for a long time. With almost no heavier elements, early gas struggled to cool efficiently, and cooling is essential for star formation. Hydrogen and helium have limited ways to release energy, so the first star-forming regions likely had to be massive, slow to collapse, and extreme in nature. Lithium existed only in tiny amounts, far too little to influence the chemistry significantly. That is why the first cosmic objects were likely very different from the stars we see today. Only later, after stars began producing heavier elements and spreading them through space, did cooling become more efficient. This allowed smaller stars to form and complexity to increase. In a sense, the early universe began with a very limited toolkit. The richness we see today was built gradually through countless cycles of creation and destruction across cosmic time. The first atomic nuclei formed before any stars existed. It is a strange realization. Nuclear physics unfolded across the entire universe long before the first point of starlight appeared. In those earliest minutes, the cosmos was hot enough everywhere for nuclear reactions, yet it was also expanding so rapidly that those reactions could not last. That balance is important. Stars can sustain fusion for millions or even billions of years because gravity keeps their cores hot and dense. But the young universe had no such confinement. As it expanded, it cooled, and the conditions needed for fusion quickly disappeared. So the first nuclei were created in a brief, universe-wide burst of activity. And then the opportunity passed. That early phase established the basic composition of the cosmos and provided the raw material from which stars would later build everything else. It is an origin story written not in flames, but in physics. Neutrinos flooded the universe long before atoms could form. These particles are incredibly elusive. They interact so weakly that trillions of them pass through your body every second without leaving a trace. In the early universe, neutrinos were produced in enormous numbers. As the cosmos expanded and cooled, they decoupled from the rest of matter very early and began traveling freely through space. If a background sea of these ancient neutrinos still exists today, it would be even older than the oldest light we can observe. Detecting it directly is extremely difficult because neutrinos rarely interact with anything. Yet their presence still matters. They influenced how quickly the universe expanded in its earliest moments and left subtle imprints on the growth of cosmic structure. In a way, the universe has always been filled with invisible travelers, carrying information from eras we cannot observe with light. Most matter in the universe is not made of atoms. It is something we cannot see, dark matter. When astronomers measure how fast stars orbit within galaxies, the visible matter is not enough to explain the observed motion. There must be additional, unseen mass providing extra gravity. The same pattern appears in galaxy clusters, where visible matter alone cannot hold the systems together. It also appears in gravitational lensing, where light from distant galaxies is bent by mass that cannot be directly observed. Again and again, measurements reveal more mass than atoms can account for. Dark matter is the name given to this missing gravitational component. It does not emit light, and it does not absorb light in the usual way. Yet it shapes the universe on the largest scales. One of the most exciting possibilities in modern science is that dark matter may be a new kind of particle. Discovering it would expand our understanding of physics beyond the familiar. Dark matter played a crucial role in forming the first structures. Long before galaxies shone, dark matter began to gather into clumps under gravity. These clumps formed a kind of invisible scaffold. Ordinary gas fell into these structures, cooled where possible, and eventually ignited the first stars.
In this picture, galaxies were born inside gravitational wells that already existed. The luminous structures we see today are like lanterns hanging inside much larger, invisible frameworks. Computer simulations show this process in remarkable detail. Starting from tiny fluctuations, they grow a cosmic web that closely resembles what we observe through telescopes. It is a powerful reminder that the unseen can leave visible patterns. Dark energy, another mysterious component, is driving the expansion of the universe to accelerate rather than slow down. For a long time, scientists expected gravity to gradually slow expansion, like a ball thrown upward, eventually falling back. But observations of distant supernovae revealed the opposite. The expansion of the universe has been speeding up for billions of years. Dark energy is the name given to whatever is causing this acceleration. It might be a constant energy inherent to space itself, or something more dynamic that changes over time. Either way, it reshapes the future of the cosmos. If acceleration continues, distant galaxies will move beyond a cosmic horizon, becoming forever unreachable, even in principle. This does not mean the universe ends. It means the observable portion of the universe becomes smaller from our perspective. This discovery also connects the largest scales of the universe to the smallest, because the simplest explanation involves vacuum energy, a concept tied to quantum physics, which we still do not fully understand. Galaxies appear to race apart because space between them is stretching. Expansion is not about galaxies flying through space like projectiles. Instead, it is the fabric of space itself expanding, increasing the distance between objects. As light travels through this expanding space, its wavelength stretches, shifting toward the red end of the spectrum. This phenomenon, known as redshift, is one of the most important tools in cosmology. It tells us not only how far away something is, but also how the universe has changed during the time the light was traveling. However, this expansion does not affect everything equally. Your body does not expand. The solar system does not expand. Gravity and other forces hold local structures together. Expansion becomes noticeable only across vast distances, where no strong forces counteract it. Seen this way, the night sky is not a static dome of lights. It is a record of a changing geometry. When we observe distant galaxies, we are not seeing them as they are now, but as they were in the past. Light takes time to travel, so every observation is a glimpse into history. Some faint galaxies captured in deep images are seen as they existed when the universe was still young, when structures were less stable, more chaotic, and rapidly forming. Astronomy is unique in this way. We cannot bring the universe into a laboratory, so instead, the universe brings its past to us. The sky becomes a layered timeline. Nearby galaxies show later chapters, while distant ones reveal earlier stages. With more advanced instruments, we are pushing that timeline further back, uncovering how the universe gradually evolved into the familiar cosmos we see today. The observable universe has a horizon, and it exists for a simple reason. Light has had only a finite amount of time to reach us. Even if something exists far beyond our view, its light may not have arrived yet. This creates a natural boundary, not in space itself, but in what we can observe. It is not a wall, and it is not the edge of everything. It is simply the edge of information available to us. The size of this observable region depends on how the universe has expanded over time, because expansion affects how far light can travel, while space itself stretches. This is why cosmology often feels like a kind of detective work. The universe provides us with a limited sphere of evidence, and within that sphere, we must reconstruct the entire story using light, gravity, and subtle patterns that survived from earlier eras. Some regions will never be seen, no matter how long we wait. This is not because something blocks their light, but because space can expand in such a way that the distance between us and those regions grows faster than light can travel toward us. In a universe with accelerating expansion, there can be an event horizon, a boundary that separates what can ever influence us from what never will. This idea is both unsettling and fascinating. It suggests that vast parts of the universe may exist, yet remain forever beyond our reach. It also means the cosmos contains a built-in mystery. Some chapters of its story exist, but they can never become part of our evidence. The early universe behaved not like a gas, but like a plasma. A gas consists of neutral atoms that mostly ignore long-range electric forces. But the early universe was far too hot for electrons to remain bound to nuclei. Instead, matter existed as a plasma, a charged mixture of particles immersed in intense radiation. In this state, electric and magnetic forces played a major role. Light could not pass through cleanly because it constantly scattered off free electrons. If you have ever seen the glow of a neon sign, you have seen a small example of plasma. The early universe was like that, but on the scale of everything. This plasma phase determined how pressure resisted gravity, how energy moved, and how the universe eventually cooled into the calmer atomic era. Within that plasma, something remarkable happened. The first sound waves in the universe. Gravity tried to pull matter inward, while radiation pressure pushed outward. This tension created oscillations, like waves traveling through a fluid. These waves moved through the hot plasma, carrying matter with them. Then, when the universe cooled and light decoupled from matter, the waves effectively froze in place. The patterns they left behind remained imprinted in the distribution of matter. Much later, when galaxies formed, They inherited this ancient structure. So when astronomers map where galaxies are located, they are not only seeing gravity's work over billions of years, they are also seeing echoes of primordial sound waves from a time before any stars existed. These patterns are known as baryon acoustic oscillations. They act like a cosmic ruler. The early waves set a preferred scale in how matter is distributed. By measuring this scale at different distances, scientists can track how the universe expanded over time. It is remarkable that a pressure wave in an ancient plasma can become a measuring tool billions of years later. The cosmic background radiation also reveals tiny temperature differences, variations so small they are measured in millionths of a degree. Yet these tiny differences carry enormous meaning. They show that the early universe was not perfectly uniform. These small variations became the seeds of everything that formed later. They also encode information about the contents of the universe, how much ordinary matter exists, how much dark matter contributes, and how radiation interacted with everything at the time. It is like a barcode imprinted on the universe itself. From this faint pattern, scientists can reconstruct a detailed picture of early cosmic conditions. Those tiny differences eventually grew into galaxies, clusters, and the vast structure we see today. In the early universe, a slight advantage in density could grow over time into something enormous. Regions that were just a little denser pulled in more matter, becoming denser still. Over billions of years, this feedback transformed tiny fluctuations into massive structures. Some regions became crowded with galaxies. Others emptied out into enormous voids.
This is why the universe appears textured rather than uniform. It also makes structure formation one of the most sensitive tests of cosmology. Change the early conditions even slightly, and the entire cosmic landscape would look different. Modern simulations begin with these tiny fluctuations and allow gravity to evolve them over time. When the results resemble real observations, it feels as though we are watching the universe build itself all over again. The cosmic background radiation also follows an almost perfect blackbody spectrum. This means its energy distribution matches that of an object in nearly perfect thermal equilibrium. The early universe, where matter and radiation were tightly coupled, would naturally produce such a spectrum. What is extraordinary is how precise this match is. Real systems usually show imperfections, but the cosmic background is almost flawless. It is as if the universe preserved a perfect thermal record of its early state. This spectrum is one of the strongest pieces of evidence for a hot, dense beginning. It is extremely difficult to reproduce such a signal through any other model, and it does not stand alone. The same early conditions that produced this radiation also explain the formation of light elements and the growth of cosmic structure. Multiple independent lines of evidence converge into the same story. And that convergence is what transforms an idea into a compelling scientific model. In the early universe, protons and electrons could not remain bound together. Heat at that time was not just warmth. It was an intense flood of high-energy radiation. Every time an electron tried to settle near a proton, a powerful photon would strike and knock it free again. The universe behaved like a restless ocean of charged particles, where electric forces dominated. Matter and light were tightly coupled, constantly interacting like partners that could not separate. There were no atoms, no chemistry, and no stable structures. Everything was energetic, reactive, and in constant motion. As expansion continued, the temperature gradually dropped. Eventually, collisions became less violent, and electrons could finally remain bound to nuclei. This transition is known as recombination. It was not a sudden flash, but rather a gradual settling of the universe. As atoms formed, the behavior of matter changed dramatically. Neutral atoms do not scatter light as strongly as free electrons do, so the dense cosmic fog began to clear. Light could finally travel long distances. The universe became transparent. This moment released the oldest light we can observe today, a relic that still fills the sky. It does not carry images, but it carries patterns in temperature and polarization that reveal the conditions of that time. Before stars existed, the universe entered a long period often called the Cosmic Dark Age. After recombination, there were no stars yet to produce new light. Space was filled with neutral hydrogen and helium gas, slowly gathering under gravity. The universe was dark in the ordinary sense, even though a faint background glow still remained. This era was a time of quiet preparation. Density fluctuations continued to grow, dark matter structures deepened, and the first star-forming regions slowly took shape. Because this period is difficult to observe directly, it remains one of the most intriguing frontiers in cosmology. Eventually, the first stars ignited, and they changed everything. These stars were not just new sources of light, they were transformative forces. Their intense ultraviolet radiation began stripping electrons from neutral hydrogen, turning it back into an ionized state. This process is called reionization. It spread gradually, forming expanding bubbles of ionized gas around early galaxies. Over time, these bubbles overlapped until much of the universe was affected. The first stars also began producing heavier elements in their cores.
When they died, they scattered these elements into space, enriching the cosmic environment. In this sense, the first stars were both illuminators and creators. They lit up the universe and began building the chemical complexity that would later allow planets and life to exist. These early stars likely formed from nearly pure hydrogen and helium. Without heavier elements, cooling was inefficient. Gas clouds had fewer ways to lose energy, making it harder for them to collapse into smaller fragments. This suggests that the first stars were likely much more massive than most stars today. Massive stars burn brightly and live briefly. Their lifetimes are short, but their influence is immense. They produce heavy elements and shape their surroundings through radiation and explosive deaths. Even though we have not directly observed a true first-generation star, astronomers search for their signatures in extremely ancient stars that still exist today. These stars act like fossils, preserving clues about the earliest era of starlight. The first galaxies began small and grew through merging. They did not start as the grand spiral and elliptical structures we see today. Instead, they formed as smaller collections of gas, stars, and dark matter within the early cosmic web. Gravity then brought these systems together. Mergers were common and often violent. They triggered bursts of star formation, reshaped gas distributions, and fed growing black holes at their centers. Over time, repeated mergers built larger and more complex galaxies. This is why images of the early universe often show irregular, clumpy shapes. They are snapshots from a chaotic era when galaxies were still assembling. Even our own Milky Way carries evidence of this history. Some of its stars originated in smaller galaxies that were later absorbed. A galaxy can be thought of as a family tree written in starlight. On the largest scales, the universe resembles a vast web. Galaxies are not randomly scattered. They trace filaments that stretch across space, connecting dense clusters and surrounding enormous voids. This structure was not designed. It emerged naturally from gravity acting over time. Slight differences in density were amplified. Regions with more matter attracted even more, while less dense regions became emptier. Over billions of years, this process created a cosmic network spanning unimaginable distances. What makes this even more fascinating is that we can simulate it. Starting from simple initial conditions and applying known physics, simulations can reproduce structures strikingly similar to what we observe. It is as if the universe follows a set of rules that allow its complexity to grow naturally from simplicity. Most of the universe is empty, yet even emptiness plays a role. Space itself appears to contain energy, something that influences expansion. This leads to a surprising conclusion. The universe is not just expanding, it is accelerating. The simplest explanation is that empty space has a constant energy density, often associated with the cosmological constant. If this is true, then as space expands, more of this energy appears. That idea reshapes how we think about the future. The emptiness of space becomes an active participant in cosmic evolution. It is also one of the deepest puzzles in physics, because our current theories struggle to explain why this energy exists in the way we observe. In a sense, nothingness is not truly nothing. It has weight in the story of the universe. The early universe expanded so rapidly that it smoothed itself out. One of the most surprising features of the cosmos is how uniform it appears on the largest scales. Regions of the sky that are extremely far apart have nearly identical temperatures, even though there was not enough time for light to travel between them in the standard picture of early expansion. This is a puzzle, and puzzles often lead to deeper ideas. One proposed explanation is that the universe went through a brief period of extremely rapid expansion very early in its history. During this phase, a tiny region that was once connected and well mixed could have been stretched to enormous size. It is like taking a small, smooth patch of fabric and pulling it outward until it becomes the entire visible surface. This idea is known as inflation. It not only explains why distant regions look so similar, but also why space appears geometrically flat on large scales. A rapid, early expansion would smooth out curvature, much like stretching a surface removes wrinkles. What makes this idea powerful is that it does not just explain uniformity, it also predicts tiny variations. Inflation suggests that small fluctuations should remain, with specific statistical properties. Those fluctuations later became the seeds of structure. When cosmologists compare these predictions with detailed measurements of the cosmic background, they are testing whether inflation is more than just a clever idea, whether it is something the universe actually experienced. Inflation may also have generated ripples in space-time itself. These ripples, known as gravitational waves, would be different from those produced by black holes today. They would be ancient, stretched across the entire cosmos, originating from the earliest moments of expansion.
If detected, they would reveal information about energies far beyond what any experiment on Earth can achieve. Scientists search for these signals through subtle patterns in the polarization of the cosmic background. The light itself carries orientation, and certain swirling patterns could indicate the presence of primordial gravitational waves. The challenge is immense. The signal is faint, and other sources, such as dust in our galaxy, can mimic it. So this search requires extraordinary care, multiple observations, and careful verification.
If successful, it would be like hearing an echo from the universe's earliest growth. The strength of the Big Bang model lies in the fact that it is supported by many independent observations. No single piece of evidence stands alone. Expansion is seen in galaxy redshifts. Light element abundances match predictions from early nuclear reactions. The cosmic background carries the thermal signature of a hot beginning. Large-scale structure reflects the growth of early fluctuations. Each of these observations uses different methods, different instruments, and different sources of data. Yet they all point to the same overall picture. That agreement is what gives the model its strength. At the same time, cosmology continues to evolve. When different measurements disagree, it is not a failure. It is an opportunity. Such tensions may reveal hidden errors, or they may hint at new physics waiting to be discovered. The discovery that galaxies exist beyond the Milky Way transformed our understanding of the universe. There was a time when astronomers debated whether spiral nebulae were part of our galaxy or something much farther away. Then Edwin Hubble measured distances using variable stars and showed that these objects were indeed separate galaxies, far beyond the Milky Way. In that moment, the universe expanded from a single island of stars into a vast ocean of galaxies. This realization changed everything. It made the question of cosmic origins far more profound. It also reshaped our place in the universe. We were no longer near the center of anything special. We were part of one galaxy among many. This discovery helped pave the way for interpreting redshift as evidence of expansion. At first, redshift was understood as motion, galaxies moving away like objects in space. This interpretation was similar to the Doppler effect, where waves stretch when the source moves away. But later, the deeper explanation became clear. The redshift is not just about motion through space. It is about space itself expanding while light travels. Still, that initial interpretation played an important role. It helped scientists accept that the universe is dynamic, not static. If galaxies are moving apart, then in the past they must have been closer together. That simple idea leads naturally to a hotter, denser beginning. Georges Lemaitre was one of the first to propose an expanding universe. Using Einstein's equations, he suggested that the universe could be growing and that it may have begun from a very compact state. At the time, many scientists preferred a static universe, including Einstein himself in certain moments. Lemaitre's work shows that scientific progress often requires both data and imagination, the willingness to follow equations even when they lead to unexpected conclusions. Over time, observations supported his ideas, and expansion became a central part of cosmology. The term Big Bang itself began as a joke.
It was originally used to mock the idea of a hot origin, suggesting something overly dramatic or unrealistic. Yet the name remained. Over time, it became a convenient label for a complex scientific model, even though it can be misleading. It suggests an explosion in space, rather than the expansion of space itself. Still, language has its own power. A memorable phrase can shape how ideas spread and how they are understood. Sometimes, even an imperfect name can carry a profound concept into public awareness. One of the most important discoveries supporting the Big Bang came almost by accident. Arno Penzias and Robert Wilson were working with a radio antenna, trying to eliminate persistent noise in their measurements. No matter what they tried, the noise remained. It came from every direction. That detail was crucial. A local source would vary depending on where they pointed the antenna, but this signal was constant across the sky.
At the same time, other scientists had predicted that a hot early universe should leave behind a faint background radiation. The match was striking. What seemed like a technical problem turned out to be one of the most important discoveries in cosmology: the detection of the cosmic microwave background. It is a reminder that discoveries do not always come from searching directly. Sometimes they appear when something refuses to go away. That faint hiss in radio antennas became a turning point in cosmology. It did more than confirm a prediction. It gave the Big Bang model a physical anchor. Without a relic background, a hot, early universe might have remained an abstract idea. But with it, the universe carried a measurable trace of its own past. This radiation was not coming from stars or galaxies. It was coming from a time when the entire universe itself was glowing. Later, more precise instruments measured this signal in extraordinary detail. Satellites like COBE confirmed that the cosmic background follows an almost perfect black-body spectrum, exactly as expected from a hot, dense origin. This result was not visually dramatic, but scientifically, it was profound. It showed that the early universe had been in near-perfect thermal equilibrium. COBE also detected tiny temperature variations in the background, slight differences across the sky that revealed the first signs of structure. These small fluctuations became the foundation for a new era of precision cosmology. Later missions, such as WMAP and Planck, mapped these variations with increasing accuracy. They allowed scientists to estimate the universe's age, composition, and expansion history with remarkable precision. From faint microwave patterns, we were able to measure the proportions of ordinary matter, and dark energy. It is extraordinary that a map of subtle temperature differences can reveal so much about the entire universe. At the same time, greater precision brought new questions. Different methods of measuring the expansion rate of the universe began to show slight disagreements. Measurements based on the early universe do not perfectly match those based on nearby observations. This tension is small, but persistent. It may point to hidden uncertainties, or it may hint at new physics beyond our current understanding. In cosmology, even small inconsistencies can be important. They may open doors to deeper insights about the universe. The early formation of elements also provides a powerful test of the Big Bang. The theory predicts specific amounts of helium, deuterium, and lithium based on conditions in the young universe. When astronomers measure these elements in ancient, unprocessed gas clouds, the results closely match the predictions. This agreement acts like a timestamp from the universe's earliest moments. Deuterium, in particular, is a sensitive indicator. It is easily destroyed in stars and not easily created later, so its abundance reflects conditions from the early universe. By measuring it, scientists can estimate how much ordinary matter exists in the cosmos. It is like weighing the universe using a fragile isotope as a scale. Large galaxy surveys provide another powerful tool. By mapping millions of galaxies, astronomers can detect subtle patterns in their distribution, remnants of the early sound waves in the primordial plasma. These patterns act as a standard ruler, allowing scientists to measure how the universe expanded over time. Supernova observations added another layer of understanding. Certain types of stellar explosions have predictable brightness, making them useful as distance indicators. When astronomers observed distant supernovae, they found that the universe's expansion was accelerating. This discovery introduced dark energy into the picture and changed our expectations about the universe's future. It also demonstrated how observations of individual events, the death of a star, can reveal properties of the universe as a whole. Modern cosmology combines many different types of data. Cosmic background measurements, galaxy clustering, supernova distances, and gravitational lensing all provide independent information. By fitting these data together, scientists can determine key parameters that describe the universe. This approach requires careful attention to uncertainties and potential biases. But when the results agree, they form a coherent and powerful model. Still, not everything fits perfectly. The tension in expansion measurements remains one of the most intriguing puzzles. If it cannot be explained by measurement errors, it may indicate that our current model is incomplete. Possibilities include new particles, changes in early energy conditions, or modifications to gravity itself. Each possibility must be tested carefully, because any new idea must also preserve the many successes of the existing model. This is how science advances, through careful testing, refinement, and sometimes revision. The universe likely has no preferred center. Expansion happens everywhere, and every observer sees distant galaxies moving away. It is often compared to raisins in rising dough. As the dough expands, each raisin sees others moving away, yet no raisin is at the center. This idea challenges our intuition because we tend to imagine events happening at a specific place. But the Big Bang was not an event in space. It was a change of space itself. Asking where it happened is not the right question. The better question is how it happened. Expansion does not mean galaxies are flying through space like fragments from an explosion. Instead, the distance between them increases because space itself is stretching. This explains why very distant galaxies can appear to recede faster than light without violating relativity. Nothing is moving through space faster than light. The space between objects is expanding. On smaller scales, gravity can overcome expansion. Atoms, planets, solar systems, and even galaxy groups remain bound because gravitational and other forces are strong enough to hold them together. This creates a universe where two things are true at once. On the largest scales, everything is expanding. On smaller scales, structures remain stable and evolve under gravity. It is a balance between expansion and attraction, between geometry and motion. Even our own galaxy is part of this balance. The Milky Way and Andromeda are moving toward each other, not away.
Their mutual gravity dominates over cosmic expansion at that distance. Eventually, they will merge, forming a new galaxy over immense timescales. This future event reminds us that local dynamics still shape the universe, even as expansion continues on the largest scales. The early universe produced almost no heavy elements beyond lithium. In the beginning, the periodic table was nearly empty. Hydrogen and helium dominated, with only tiny traces of lithium. The universe cooled too quickly for heavier elements to form in that early, global phase. This simplicity had profound consequences. Without heavier elements, gas could not cool efficiently, and cooling is essential for structure formation. Everything complex, from rocks to oceans to living systems, came later. The early universe provided the simplest ingredients, and stars became the factories that built everything else. Inside stars, nuclear fusion created heavier elements step by step. Hydrogen fused into helium. Helium fused into carbon. Carbon led to oxygen and beyond. Iron marked an important boundary. Fusion up to iron releases energy, but beyond iron, it requires energy. That limit shaped how stars live and die. The elements that make up your body, your planet, and the world around you are the result of countless stellar generations. For elements heavier than iron, even more extreme events were required.
Supernova explosions and neutron star mergers created environments where nuclei could rapidly capture neutrons and build heavier elements. Gold, for example, is likely formed in such violent cosmic events. These elements are not ordinary. They are the products of rare and powerful processes. The universe is not only a place of calm expansion, it is also a place of transformation through extreme events. Black holes may have formed early and grown rapidly. Massive stars in the early universe could collapse into black holes, and under the right conditions, these black holes could grow quickly by accreting gas. This may explain why we observe extremely massive black holes very early in cosmic history. Some theories even suggest that black holes could have formed directly from dense regions in the early universe, without stars as intermediaries. These so-called primordial black holes remain a possibility, though they are still under investigation. If they exist, they could even contribute to dark matter. The universe may be filled with structures we have yet to fully understand. The geometry of the universe appears to be very close to flat. This does not mean the universe is small or simple. It refers to how space behaves on large scales. In a flat universe, parallel lines remain parallel, and triangles follow familiar geometric rules. Measurements of the cosmic background show that space is remarkably close to this flat geometry. This result is deeply connected to early expansion. A rapid inflationary phase would naturally drive the universe toward flatness, smoothing out curvature. However, flatness does not tell us whether the universe is finite or infinite. It is possible for space to be flat and still wrap around itself, like a higher dimensional version of a looping surface. If that were the case, distant regions of the universe might repeat in subtle ways, though no conclusive evidence has been found. This is one of the many ways the universe may be stranger than it first appears. The Big Bang model does not explain everything. It describes how the universe evolved from an early, hot, dense state. But it does not fully explain why the fundamental constants of nature have the values they do. Why is gravity as strong as it is? Why do particles have the masses they have? Why does the vacuum behave the way it does? These questions remain open. The model also does not fully explain why there is more matter than antimatter. This imbalance is essential. Without it, everything would have annihilated into radiation, leaving no stars, no planets, and no life. Understanding how this imbalance arose is one of the deepest challenges in physics. Scientists refer to possible mechanisms as baryogenesis, processes that could have tipped the balance in favor of matter. Any successful explanation must satisfy strict conditions, and many ideas are still being explored. The earliest moments of the universe remain beyond direct observation. We can see back to when the universe became transparent, and we can infer earlier conditions through indirect evidence. But the very first fraction of a second is still hidden behind a theoretical boundary. To fully understand that era, we would need a theory that unifies quantum physics and gravity, something we do not yet have. Even so, the universe has left behind clues. Light, elements, and large-scale structure all carry information about early conditions. These independent lines of evidence must agree, and when they do, they form a consistent picture of cosmic history. The universe is still expanding even now. Expansion is not just something that happened in the past. It continues in the present and will shape the future. Over immense timescales, expansion will influence how structures evolve. If acceleration continues, distant galaxies will eventually move beyond our observable horizon. Future observers may see a much emptier universe. They may not detect distant galaxies or even the cosmic background radiation as we do today. This suggests that we live in a special observational era, a time when the universe is still visible in its large-scale richness. In the far future, much of that information may be lost from view. The night sky itself could become quieter. Yet even then, the universe will continue to evolve. Local structures will persist, stars will form and die, and gravity will continue shaping what remains bound together. The Big Bang is not just a story of a beginning. It is a story of change, a universe that continues to unfold over time. From a hot, dense origin to a vast cosmos filled with galaxies, light, and structure, everything we see today emerged from simple beginnings. And within that vastness, there is space to slow down, to let the day fade, to release the weight of thoughts, to rest inside something far larger than any single moment. If you are still awake and curious, another journey is waiting for you. And if these quiet explorations bring you comfort, you might choose to stay a little longer, to like, to subscribe, or to share a thought. For now, there is nothing you need to do. Let the images soften. Let the ideas settle. Let your breathing slow.
and let your thoughts drift like distant galaxies, moving gently outward, becoming quieter as they go. You have done enough for today. Sleep well, and good night.